Hey, do you like multiplication?
Mid.
Uh,
Is that okay?
yeah, it's cool. I like math.
Cool.
Hey math lovers, let's go over 8.4 normal distributions. What's our learning targets? The standards for mathematical content, students will use the mean and standard deviation of a data set to fit it to a normal distribution and estimate population percentages. Recognize that there are data sets for which such a procedure is not appropriate. Use calculator spreadsheets and tables to estimate areas under the normal curve. And SIC6, evaluate reports based on the data. How can you meet this standard? I can use the mean and standard deviation to analyze normal distribution data. By using technology. All right, let's go ahead and go over this warm-up. And you go ahead and try that. One tip I want to tell you is that standard deviation for the population is this symbol, which we learned previously was called sigma. It's just standard deviation. Variance is just taking the, that's just abbreviation, variance is taking the standard deviation and just squaring it. Okay, go ahead and try that and then press play and then we'll do it together. Alright, it tells us to find the variance and standard deviation for each set of data, round to the nearest tenth if necessary. I'm going to plug in those three numbers into my graphing calculator. I'm using Graphing Calc 83 there. And I'm going to go to Stat, Edit, and go to the very top of your list, or you can just click there if you have a touchscreen tablet. Clear, Enter, Clear, Enter. And then we're just going to input those numbers. 8, 2, oops. Can make a mistake like I do, that's okay. Enter, 2, Enter, 10, Enter, 6, 9. And then while I'm at it, I'm just going to do the other ones as well. 78, 78, 95, 87, and 62. And then list 3 over here, I got 4.5, 2.5, 4.5, and 2.5. Okay, so it does have 5 numbers in the first list, 5 numbers in the second list, and 4 numbers in the third list. So let's get out of here. Second mode, or to quit. And then I'm going to press Stat, Calc, 1 bar stats. Remember, if you just press Enter here, the default is just list 1. Okay, here I have 2.8. Looks like ox, but it's not. That is my 1 bar stats there for my first list. Okay, what you can do is you can just take that number, 2.8, I don't know, round it to the nearest 100, and then square it. It's over there, top left of the 7. And this gets me approximately 8. So here my variance is going to be 8 and my standard deviation 2.8. Okay, so do the same thing for the other one. Stat, Calc, 1 bar stats. And now I need to put list 2 in there. So there's 2 ways to get there. You can press second stat, or I'm just going to press second number 2. You don't need to close parentheses. And there I have a standard deviation. Looks like, again, aux right above the n is 11.00, so 11. And then if I take that number and square it, take this number 11.009 and you square it, you get approximately 121.2. And I just took that number 11.0, because remember it was like 0.9, and that number is less than between 0 and 5, so that number stays. So I don't really need those numbers. And the last one, stat, calc, 1-bar stats. I need list 3. Let's do the second method. Second, stat, list 3. Enter. Okay, my standard deviation there is 1, and if you take 1 and you square it, it's just what? 1. So let's go back out here. Oops, I don't like using that color. Okay. Which of these numbers were clustered more around the mean? So the word mean, let me draw. This is our ghost, the normal curve. We're going to learn that today. But mean is a measure of center. It actually goes here in the middle. So where is that data close around the middle? Well, remember, standard deviation and variance are measures of spread. Measure of spread. So if it's a small number, such as 1 and 2.8, they're going to be around the middle. But if they are a big number, you like that color? Like 11, then they're really far spread out. Okay, little spread around the center like jam, strawberry preserves, or if it's a large spread, it's really spread out. So which of the sets were more clustered around the mean, which means they would have a small spread? I would say in that one, number 3 had the smallest one. So we'll warm up number 3. And then which one was more dispersed? That one's just more spread, widely going left and right. That would have been warm up problem number what? 2 had the largest one. Okay, so now this question number 5 tells me to create a dot plot. And what I'm going to do is look at the range. I'm going to look at the largest number and the smallest number. I see it's like pretty much like 10, and I see a 5. So what I'm going to do is I'll put 5, 6, 7, do my best to equally distribute them, 9, and 10. And a dot plot just basically means we're going to put a dot. And as you do that, go ahead and put a check mark so you don't forget where you put it. 6.2, 7.6, there's a 5, 7.1, 9.4. And it is important to have the same size of a dot. 6.6, 8.3, 7.8, 5.7, 9.9, 6.1, and 7.3. Okay, so here is my dot plot. And that didn't give me great results. So another way of creating another dot plot is putting them into bins. Putting them into bins. And this time, I'm going to say all the numbers in here are between 5 to 5.9. And I'll say 6 to 6.9. And 7 through 7.9. 8 to 8.9. 9 to 9.9. And I'm going to do it again, so 6.2. But I'm going to just put it above the tick mark this time. 7.6 is in this bin, like a drawer, kind of like, you know, you put away your clothes. 7.1. See what I did there? 9.4. 6.6. 8.3. 7.8. 5.7. 9.9, and this is giving me a better visualization. You're going to see this 6.1 and 7.3. And what we like to do is then draw mountains over these peaks and valleys of the mountain. And that looks a little bit better on my data. Okay, let's try the same. Let's try the same. Let's do some magic. Watch this. Say the words. Magic. Magic. And let's go ahead and this one, let's go ahead and make a histogram. And the histogram is the same idea, but now we can just indicate it. There's like 1, there's 2, 3, and 4. So there was 2 over here. Do you see that? 1, 2. And then in the 6.9 bin, there are 3. And then there's 4 over here. And then 1. And then the next bin there was 2. I want to show you guys this. This is really cool magic. Let's see if I can get it. I don't think I was able to grab it. Let's see. Pretty close. Do you see what I was trying to do here? What I was trying to show you is that basically the distributions, the graphs, are pretty much the same for a dot plot or a histogram. Okay, that is our review. All right, a normal distribution is and we're here doing the launch. The normal distribution is a continuous, symmetric, is what goes into your fill in the blank, symmetric, bell-shaped distribution of a random variable. Now let's get this into real life. For each animal species, gestation time, gestation just basically means pregnancy. So in blank number 2 goes pregnancy. It can be described as a normal distribution. All right, what are my 3 animals here? I have a pig, hamster, and a dog, which is like a specific one. It's a beagle. Beagle? Beagle. Different animals carry their young in the womb for different amounts of time. The average gestation or pregnancy time, how long the baby's inside the animal, for a species is usually related to their body size. The gestation time for each species can be described by a normal distribution. Our normal distribution is a continuous symmetric bell-shaped distribution of a random variable. All right, there are our 3 babies. This is a normal curve. It looks like a bell, kind of. I don't know, that's what they call it. About 60% of young are born within 1 standard deviation of the mean time, and 95% of the young are born within 2 standard deviations of the time, right? And the baby could come in the middle here, And the mean just means the average, so baby can come late or baby can come early. You know, most of my babies were born early. Here is the mean time. So on average, a hamster will give birth every, when they're pregnant, will come in 16 days. And then the standard deviation basically means, you come up to one other, it will take 3 hours more or 3 hours less. And then most of that data is within 3 hours, right? Beagle holds a baby 65 days, and their standard deviation is 5 hours. And then a pig, which is a lot bigger, you guys can see the size, average is 116 days versus 2 days. Long and short. The longest gestation period for an animal is a possum, 11 days, and an elephant, 645 days. And then there, blanket number 4, the average length of a human gestation is 265 days. I did not know that, even though I have 6 kids. I think it just means that it's like 9 months. All right, let's go ahead and move on to our exploring the probability distributions. All right, so we said the answers were symmetric. Symmetric is like your face, and you cut it in half. A heart is symmetric. If you put a mirror right there, cuts it in half. Does it make sense? And then we said for each animal species gestation time, which is basically another word for pregnancy. Did I spell that right? And the 3 animals shown were a hamster, pig, and a dog, which was a beagle, and 267. All right. All right, let's do some exploring here. And I'll just give you the first one to help you. If we roll 2 dice, it has the numbers, it has the numbers 1 to 6, right? So if I do something like this, and the sum just adds them together, then I get a 4. So can you list them all out and then answer questions 2 to 4? Click on the word simulator here, and you're going to do something, draw a picture, and then we'll fill out the rest there. All right, let's go over this simulator. Simulator is just a way of computer, instead of me rolling the dice many times. So again, I sum here, that would be 2. So hopefully you made a prediction, all different sums, and which one do you think is more likely. Are they all likely to be rolled? And if not, predict which number will come up the most. Let's go ahead and press this one a couple of times. Okay, so 4 plus 4 is 8, so it's making a histogram here. Just press it a couple of times, 11. And let's press 10 a couple of times. Now it's rolling 10 dice at a time, so now next 10 dice will be 36, and they just add them to the different bins, right? So 9, that one went in there. And what do you guys notice is happening? Let's do 100 a couple of times. And then you can press 10,000 a couple of times. Boom, 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 boom. I don't know, let's go crazy. Okay, so let's just draw that on our graph here. Okay, so hopefully you would have said that the different numbers that can be added up are 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. You could have made a prediction, I don't know. Maybe thought 6 was the most popular number. Well, whoops. Will these all come up? Maybe you said yes, maybe you said no. I'm not sure which one you wrote. But if you wrote no, which one do you think came out most? Maybe you're like 8. And then we did the simulation there, and let's go ahead and draw ours. If I can. I don't have the numbers, they were too big. But there was nothing rolled in the ones. And it kind of just kind of looks like there's these staircases, this histogram. to review the graph distribution that you drew above, this is called our experimental probability. Why? Because we did something. We do. While this one is actually, there's actually 36 outcomes. So a 7, let's see, 7 can we come up with how many ways? I think it's, let's find out, double check. So you can have a 1 and a 6, or 6 and a 1. You can do 2 and 5. Or 5 and 2. You can have 3 and 4, or 4 and 3. And so there are, that would be 1, 2, 3, 4, 5, 6. And there's 36 outcomes, so you get 1/6, which is like 17%. So that one, this one is called our theoretical. Should have came up 16% of the time. All right, let's go ahead and move now to 8.41. All right, a probability distribution, and a distribution is just a fancy word for a graph. A graph is a mapping of each outcome of a statistical experiment to its probability occurrence. Okay, so I have two graphs down here, and I want to define a couple of things out here. Okay, this one on the left side, this one is called a discrete, let's make that thicker, discrete random variable. That's this graph here in blue. And basically, some key things is that it's finite. You know, Desmos wanted to find the infinity stones because infinity means he lasts forever. Well, this is finite, so that's the opposite of that. So human beings are finite. We're only going to live up to maybe 100 years old. Here's another one. It can be counted. It can be counted. Okay, so another thing is that it's graphed. What do you notice? Are they touching or not touching? They're not touching. So the graph has space. Between them, because you can't have an in-between. You basically, if you think about it, you couldn't roll a sum of 7.2. Okay? Alright, let's try another one. Let's try this one. You guys know what the other one's called? Yeah, that one over there is called a continuous random variable. Continuous random variable. And what are some characteristics of this one? It could be any value. Like I got a new used car and I'm trying to keep my miles per gallon. So it's this one, kind of messy, this purple one over here. And I'm trying to keep my miles per gallon like over, 18. So right now I'm getting like 18.9 miles per gallon. Does that make sense? The sum on the blue side was, a whole number. And this one can take any value, decimals or fractions. Okay, what do you notice about our graph? Our graph is basically a histograms. Which is basically area under a curve. That's it. Under the curve. And over here, we basically had bar graphs. Okay? All right, so we have these things called outcomes. And an outcome is just the result. What happens? When I roll the 2 dice, the results are individual ones. It could be like a sum of 12, or maybe like 23.9 miles per gallon. Then we have something called a sample space. What is a sample space? All outcomes. You kind of know all the samples that can happen when you roll 2 dice can either you add them up. It could be 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Maybe your car is like going, you don't really accelerate. You have optimal conditions, and you can go all of the miles per gallon my car can get. And the last one, what color have we not used? Let's use orange. Is, well, big one, probability. And probability is just the likelihood of an event. So for example, the probability of rolling a 12 is 1 out of 36. Maybe the probability of the time I'm driving my car and I want to get 24 miles per gallon, maybe it's pretty low. Maybe I'm getting like 15. Alright, let's move on to key concept. Conditions for probability distributions. The probability distribution of a random variable x. So again, the x can refer to the sum of 2 dice. It could be miles per gallon on my Honda Pilot. It must satisfy these conditions. The probability of each value of the random variable must be between, well, think about like rain. The probability it rains is between 0 and 100%. Or 0 and 1.0 as a number. And the sum of the probabilities of all the values of x must equal also 1 when you add them all up. Okay, let's think about this. Let's do these examples over here. Example number 1. Classify each variable as a discrete or a continuous. I have the number of songs on random selection of smartphones. Okay, so question, can I count, look above, discrete is where we can count, let's do that color coded. You can count, that's a number, or purple, this could be any value. Those are from our notes above, right? So you can count the number of songs, right? The number of songs on a random selection of a smartphone is discrete because the number of songs is countable. All right, let's go ahead and try the second one. The air pressure in a random selection of basketballs. Well, let's just say I go up to a basketball and it measures, I don't know, 7.5. Or it can be 8.2. It can be 9.9 pounds per square inch. Therefore, air pressure is continuous because it could take any value within a certain range. So there's a bunch of range of numbers. Go ahead and try questions C, D, E, and F, and then we'll go over theirs together. All right, if you're a swimmer, you're measuring your time. So the times, someone can be going fast, someone can go slow, just like the Olympics we just saw, so continuous. The number of students in class, well, although they can take any value, I'm actually counting them, so that would be discrete. Individual archery scores, same thing. I don't know what the numbers are. They score 5,000, maybe 5,002. You can count them, so that is discrete. And the amount of water in a bottle, you might think, well, they all have the same 16.9 ounces, but that's not true if you actually measured all of them. So this one would be continuous because there is a range that which we would find. Okay, go ahead and do questions 1, 2, and 3 as our practice, and then go ahead and press play when you want to see the answers. All right, let's go over question number 1, the number of texts received per week. Well, although there might be a range of numbers, you can count them. And they are whole numbers, right? You don't receive 2.4 text messages from your special someone. Question number 2, the number of likes for a web page. Can you count those? Yes, you can. That is discrete. And the height of a plant after a specific amount of time, well, they might have a different range of values. You might have 6 inches, 12.2 inches, 11.4, therefore that would be a continuous.
To frequency. So let's go ahead and describe what a frequency table is. A frequency table shows okay, so I'm going to use count. I'm going to change the colors there so you can see the emphasis. Frequency is a table of shows the count of individuals having each data value. And to emphasize count or frequency, you can just like count, right? How many, if you look at your desk, how many wires do you have on there? So if I look at I might have, this is my tally marks, right? I have 2 of them. I'm just counting. Or how many keyboards do I have? I actually have 2 keyboards on my desk right now. All right, let's go to frequency table. A relative frequency table. A relative frequency table shows, all right, here's the big word, the proportion or percent. So if you're just doing this on regular paper, you can just go back and highlight it. That'd be a good idea. Of individuals having each data value. All right, here is an example. Which would you rather be? If you could pick only one of these, which would it be? Go ahead and check one of those, and then I think I'd rather just be, to me, happy. And if we got a data set, right, so let's move on page 3 here. Here's the data from 40 randomly selected high school students around the US. So here, each one of these are data. And this is how students respond. So I'm not sure how you responded. It says tally or count up for each status. What is that called? Look above. To count or tally. this would be our frequency table. Wow, so bad, sorry. Again, first time using this pen. So this, now I'm going to highlight in blue, this is our frequency table. So when you tally or count, let's write the word count over here, or frequency. Okay, we're going to have to count how many famous people. I'll do one and then you do the rest, okay? Here is a practical thing when we're looking for the word famous. To tally, you might just mark them as you go, but I'm actually going to use my pencil and check each time I see the word famous. And the reason why you do this is so that you don't skip any of the data. You don't leave anybody out. So 1, 2, 3. Just going down 4, 5, 6, 7. So there were a count of 7 for those who were famous. Go ahead and just count up the rest and then go ahead and make a total of those. Go ahead and press pause, and then when you're done, press play. All right, so if you go ahead and do that, you'll get 21 rich, 4 healthy, 21 happy, 4 healthy, 80 rich, and then you have a total of 40. This sounds so silly. You're like, oh, if you did make a mistake, okay, this is something very practical in statistics, just counting. And like I said, use those check marks, and you should have a total of 40. All right, what happens when I now want to calculate a proportion or percent? Okay, let me write another word over here. Proportion or percent, you get those from fractions, right? This never goes away, fractions, okay. So this is called, when I turn in the numbers above to a fraction, this is called a relative frequency. Okay, so let me do this. Let's do a different color for the total. See if I can write in here. Again, new pen. Figuring this out, guys. Give me a break, okay? All right, so what we're going to do is basically make a fraction. So let me show you how to do that. So the total, I like to write my fractions this way, 40. That's the total, right? And then let's do famous. There are 7 out of 40, okay? So there's my fraction. Some of you guys may have done something like this. I do not recommend the horizontal, so I prefer this one, the vertical versus the horizontal. This is perfectly okay. So now we got to make it a, we go from fractions to decimals. I have no calculator function here. So put in your calculator, 7 divided by 40. 7 divided by 40, and your answer is going to be 0.175. Okay, so how do we make this? Because this is up here, it doesn't say fraction, it doesn't say decimal, it says a percent or a proportion. So now, so we go from fractions to decimals, and basically what you're doing to get a decimal is you are multiplying to get a percent. You are taking the decimal and you're multiplying it by 100. So you can put in your calculator times 100, don't touch your calculator. And what this does is you're moving the decimal place 2 places, and your answer is going to be 17.5%. So let's review really quickly. You take the number of famous and you put it over 40. And then you're doing division there, and you'll get a decimal. You should never have a number over 1 here. So this is like 17 cents. And then to go from a decimal to percent, you multiply by 100. Go ahead and finish the rich, healthy, and happy, and then press play to check your answer. All right, so here's my answers. Just trying for a different color so I can use it. the top parts of my fraction, the numerators, all of these numbers are adding up to be 40, right? Here's my decimals. If you add up all of those decimals together, think of money like change, 17.5 cents, 52 cents, 10 cents, 20 cents. You add them all up, they should be $1. So a decimal, most of the time, is never going to go over 1 in general. Probably about 95% of the time in this class. If you add up all the percents going down, they should add up to be 100%. So now it's time for your homework. Hopefully this was helpful for you. Good luck, guys.
All right, let's go ahead and create a relative frequency graph here. And you have your famous, your rich, your healthy, your happy, and over here I see the max of around 52%, so I don't know, 10, 20, 30, 40, 50. And we can title this one Preferred Status. I think I would prefer to be happy. So famous was 17.5. You can go below 20 there. You see that? You can use that little dotted line that I kind of drew. Rich is 52.5. Then we have healthy at 10%. Should have color coded those. 17.5, 52, and then yellow is 10. Healthy and happy is 20%. And that matches the information we just wrote in our notes, that if you add all those up, that should be what? Equal to 100%. Let's go ahead and try the example below. All right, for a relative frequency, all we have to do is get the total. So if I count all those up, there is 200. So essentially what you have over here is 150 divided by 200, and this will give us 0.75. 40 divided by 200 will give us 0.20. 9 divided by 200 will give us 0.045. And 1 divided by 200 is going to give us 0.005. So essentially, if you add all this up, you will get 1.00. Okay, so title of this one is Prizes Won. And I have the prize amount. And we had $5, we had $50, we had $100, and $1,000. And then over here, I have my probability. D. And again, the max I see there is 75, so I probably want 8 of them. 1, 2, 3, 4, 5, 6, 7, 8. Okay, let's go ahead and do this one over here. So that's 0.75. That one, you want your bars to be of equal width. I have 0.20. I have 0.045, so it's 0.10, so it's like half of that. And then you can barely see it. That's less than 1%, right? I don't know, it looks like a bar, it's just a line. And that's what we got here. This is our graphing our probability distribution. All right, let's go ahead and go over this next question here. All right, 8.43 Misleading Distributions. A business publishes a report saying that most of its employees earn at least $40,000 annually. When asked to show the distribution of salaries, they provide a probability distribution. Identify any flaws in the representation of the probability distribution. All right, what are we trying to do here? The company is trying to provide evidence, that their wages are fair. Okay, do you think the company wants to pay people lots of money? Probably not. So we could say that the company benefits from a distribution. Remember, distribution is just a statistical word for like a graph. A distribution that makes salaries of $40,000 to $50,000 appear significantly more than the lower amounts. Right? If you look at that histogram here, this number, it looks like it's really high compared to what's happening over here. But the way they scaled it, one thing I notice is that the x-axis, the scale for x-axis is misleading. Well, it seems like most bins, these are called bins down here, most bins are distributed evenly. The outliers. Okay, what's an outlier? Outlier, something way out there. Because the outliers are kind of hidden in the last bin. So let me try to draw a line. So what happens if we change the bins to 0 to 40K, right? And then you would have something like way up here. And let's just say you did 41 to 80K. And let's say you have it like, looks like that. And then you have 81K to 120K. Now my graph is kind of saying like, you know what? Oh man, that company, they don't pay a lot of money. Look where all the numbers are at. They're in the lowest bins to the far left. Does that kind of make sense? So just your scaling can really change things. Go ahead and try question number 5 below about basketball teams, and then go ahead and press play when you're ready. An athletic director made a probability distribution of the heights of her team's basketball players and distributed a flyer that claimed that the majority of the players on the basketball team are 71 inches or taller. Identify any flaws in the representation of the probability distribution. Look at the graph. What is she trying to say? My team is tall because there's a bunch of people in the taller range. You know, I'm almost 6 feet tall, and that would be 12 inches. Times would be 72 inches. So that's like a 6 foot tall player. Okay, what do we notice? They're missing something, and we have it up here. I call it an earthquake. It's missing an earthquake because they're not saying the data, the probabilities of 0 to 24%. Okay, so we can say the answer is what's wrong with this, what's the flaw in the scale, which axis? Of the y-axis, misleadingly shows the differences in probabilities. So I'm telling you, look right here. Let's actually make one so you can kind of see why. Okay, let's do this again. This time, I'm going to have it at tens. And let's see if this changes what it looks like. I'm going to do the same thing. 61 to 65, 66 to 70s, 71 to 75, 76 to 80. And they're saying they're about 24. 24. And maybe this next one is 24. Does that make sense? Like, that's 0.25. And how about blue? Next one is 0.26. Do you see what they did there? And the other one's 0.26. So, is this now showing that all the players are like super tall on the team? For whatever reason, maybe she wants to tell the other coaches. No, they're all pretty much evenly distributed, but because she kind of lied with her statistics, right, using math to kind of convince other people otherwise, that was incorrect. All right, let's talk about the 8.44, the law of large numbers. The key concept here for the law of large numbers is as the number of trials increases, the experimental probability approaches the theoretical probability. Think back to about our rolling the dice. The normal distribution The graph of a normal distribution is continuous, okay, bell-shaped, so that means it can pick any number, a range of numbers, bell-shaped. You know, I keep asking that question, ooh, do you believe in ghosts? That's my ghost. And is symmetric with respect to the mean. Okay, so the mean is the measure of center, it's right there. Symmetric, it just basically means this is half and this is the other half on the other side. So I like their horns, I don't know. The mean, median, mode are equal and located at these are what? Measures of center. They're pretty much the same. So when you're using the calculator and you're getting just the mean, median, mode, and all those numbers are pretty much the same, then it's normally distributed. The curve approaches but never touches the x-axis. So they're talking about like right there, they shouldn't touch. And the total area under the curve is equal to, what was the number we had before? 1 or 100%. Think of weather, right? If it's going to rain 5%, that means that it's sunny 95%, or won't rain the other way. All right, let's try this problem here about soccer. All right, we have the total number of goals scored by each player of a soccer team during the season. Create a histogram, so that means they're touching, and then determine whether the data can be approximated with a normal distribution. Okay, let's put the title, goals scored per player. Okay, and let's pick the smallest number and the biggest number. So I have 0 to 11, looks like. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And down here is the number of goals, and this is our frequency. Remember, frequency just means our count. Okay? So let's just count. And again, this little technique of just check marks are super helpful. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So it looks like zeros are the most. So let's go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So 14's up here. Okay, let's do, why do I do that? Put blue check marks. Are you following what I just did? Blue check marks, and I drew a black box. Okay, let's try, now it got messy. Goodness gracious. Okay, there we go. All right, let's try green now. Let's do the ones. 1, 2, 3, 4, 5, 6, 7 ones. And 1, 2, 3, 4, 5, 6, 7. So that'll be a right here. Okay, and the twos. 1, 2, 3, 4, 5 twos. Oops, a little bit lighter there, or equal width. Let's try a different color here. Let's try purple. And what do we got next? Threes. 1, 2. And I just didn't write down all the numbers there. Do you see that? Okay, any 4s? No. 5. I see 1 right there. Any 6s? No. 7s? No's. 8, how many 8s? Same thing, 1. How many 9s? 1. It's supposed to be red. 10, and then you have an 11. Okay, now this is the fun part. You get to kind of put you kind of go over the peaks here. Okay, does that look like something where all the data is in the middle? So we say this data set is skewed. And to remember, the skewness is where the tail is, and the tail is where? This is here on the right, skewed right. It means there's no data to the right. Thus, the data cannot be approximated with the normal distribution. Okay? All right, go ahead and do the same thing on the next problem here, and then go ahead and press play when you are ready to see the solutions. All right, question number 6 about the track times. Now this one's a little bit tricky because they're all in the 14s. So if I were doing this, you can do something like, maybe over here you have 14.0 to anything that's about 14.1, 14.2, 14.3, 14.4, 14.5, anything up to 14.6, 14.7, 14.8, 14.9, and that'll be like 15. And you can just do like a little, so time measured in seconds. And what else we got up here? 110 meter hurdle race. And then this would just be our frequency. Okay, so 14.75 I'm going to put in this bin right here. And I'm just going to do a tally down there. 14.77, 14.31, 14.83. It's between 14.8 and 14.9. 14.84, 14.35, 14.69, right in there. 14.63, 14.74, 14.2, 14.25, and 14.93. Okay, so I do not want to put up here 10. That would be a bad number because my numbers would be kind of squished and doesn't really show the data. Does that make sense? So maybe you do it by, I don't know, one, they got to be equally spaced, 2, 3, or 5. Not a great job over here. Okay, so we have 0, and then we have 1 in there, and then we have 2, 0, 0, 0, and then 2 in here, and then 3 in here, and then 3 in there, and then 1 in there. And then just come back here and try to draw over what's happening. Okay, now pay attention. You're going over the peaks, but you also have to go down here because there's no data, right? This one is, I would call it bimodal. There's kind of like two peaks here. And that's not unimodal and symmetric. Okay? So I would say, just use the same sentence as the last problem. Data set is not, that's an N, normally distributed. Okay? Okay. Let's move on to 8.45. We're going to talk about the empirical rule. Okay, let's just do some basic definitions again. Right here in the middle of a normal curve is something called the mean. And we've talked about previously in a previous video, this is the mean for the population, and this one is called a sample mean with X bar. And then we talked about how standard deviation is here in green. Standard deviation. It is a measure of, they call it spread. How far apart is the data from the center? So I'm just going to call that spread. And in the blue, mean is a measure of the center. Okay, I'm going to talk about the empirical rule, but before I do that, I want to mention one idea. Area under the curve equals 1. So basically we talked about this ghost, right? And if you shade this all in, that is equal to 1. Okay, so the big one is called the empirical rule. And in the empirical rule, 1 standard deviation, remember -1 standard deviation, the symbol for standard deviation is here with the O with the little tail, and positive standard deviation. Positive just means you're going towards the right. Is this area. Alright, so this whole area is a total of 68%. Let me shade that in with a yellow. So everything that I'm shading in here is 68%. Now, you need to know this. If the mean, the dark blue line, cuts it in half, that means each of these are 34%, because 34 plus 34 equals 68. So if I said how much of the data is 1 standard deviation above the mean, that would be towards the right, that would be 34%. If I said what is the area, what is the percentage of the area between 1 standard deviation, we talked about between is between 2 locations, that's -1 standard deviation plus 1 standard deviation, 34 plus 34 is 68. Okay, the next part of the empirical rule is within 2 standard deviations, so here again is the mean. This would be a +2. This would be a -2. And these numbers are always, so in empirical rule, always between 2 standard deviations. This area I forgot to draw the mean. So total, this whole area is going to be 95%. In red, the shaded red area. And if you divide 95 in half, you will get 47.5% each. So the left side is 47.5, the right side is 47.5, and you add the 2 reds together, you get 95%. Now, you might come into a situation that looks like this. Whoops. Let's try that again. there's the center. And let's just say you're at if you know this blue region here represents 34%, then this green region, 47.5 minus 34 gives you 13.5. Why? Because the green area, if it's 13.5 and the blue area is 34, if you add those two together, you will get 47.5. So that, going that direction, remember, is 47.5. Okay? And let's do the last one. Let's do purple. The last one is within, from the center, 3 standard deviations. Let me count those out loud. 1, 2, 3 standard deviations. And if you go towards the left, 1, 2, 3. Basically up here. Let's shade that in some kind of color here. Let's choose green. So everything in green, this here represents, in green, 99.7%. So again, the empirical rule is 68, 95, 99.7. So let's just say you divide 99.7 in half. Divide it by 2. So 99.7 divided by 2 gives me 49.85. 49.85%. Okay, I do want to point out an area that we did not talk about is this area in red. These are called the tails. And we talked about how the area under the curve is 100%. And if I do it for this problem, let's say I subtract 99.7. That means the two tails together equals 0.3% together, the two reds. So 2 reds equals 0.3%. If you divide it by 2, you'll get one of these reds equals 0.15. So if you add up all these areas together, let me get a different color. Let me get you yellow. 0.15 plus 49.85 plus, that one's to say 49.85. That's what I didn't want. No. Let's try that again. Okay, so 0.15 plus 49.85 plus 49.85 plus 15 will give you 100%. Okay? So this is called the empirical rule. So basically in the next problem set, you're going to do the same thing. You're going to do the shading of region, and then you'll use the empirical rule and kind of divide them up to figure out the estimated percentage. All right, here's our example. A normal distribution has a mean. So again, the mean is a measure of center. It goes right in the middle. And then we're going to say our standard deviation is 6. And this is what it means. You can keep adding 6 this way, and you can keep subtracting 6 this way. And that would give us scores like 42 plus 6 would be 48, 54, 60, and then you're just going to subtract. So 6, 42 minus 6 would give me 36, 30, and 24. Okay, so it says find the range of values that represent the middle 95% of the distribution. 95%, remember, one standard deviation away would have been 68, but 2 standard deviations away is how much? 95%. So basically what we're trying to look for is around 2 standard deviations away. 1, 2, 1, 2. So that would be between 30 the middle 95% of the data is represented by the range of what numbers? Of 30 to 54. Okay, part B, what percent of the data will be greater than 36? So they want to know this side. Okay. Now, if you, let's use, I'm using green. If one standard deviation away, if this represents 68%, that means the other 2 regions are equal because it's symmetrical. So you can do like something like 2x plus 68 equals 100. So you subtract 68, got 2x equals 32, and then x equals 16. So this left side is 16%, and this side is 16%. But if you think about it, what I'm trying to find is that red region, right? So the yellow, I guess that's a bad way of coloring it. Yellow, let's write that, yellow plus red equals 1. And if you know the yellow is 16, and you're trying to solve for the red, 0.16, and you subtract 0.16, you're going to get the red equals 84%, 0.84 or 84%. And a second way you know that is because you can just add 68 plus 16 gives you 84. Okay, go ahead and try number 7. You gotta draw out a picture, label everything, and then go ahead and press play when you're ready to see the problem. Alright, here is my normal distribution curve. That's the middle. 1, 2 standard deviations, 3 standard deviations away. My mean is 186.4. And this is going to be fun. You have a standard deviation of 48.9. So I'm going to add 48.9. I get 235.3. And then I'm going to add 48.9 again and get us 284.2. And then you add 48.9 again and you'll get 331.1. And then I'm going to go back from 186.4 and subtract 48.9 and get 137.5. And I'm going to subtract 48.9 again and get 88.6. And then subtract it one last time and we have 39.7. Okay, what range of values represents the middle 99.7%? So based off the empirical world, this is how many standard deviations away. This is 3 standard deviations away. Let me count them. Now, it does not matter. It's kind of like the absolute value. It does not matter which way I go. You kind of have to go both. Ready? 1, 2, 3. From the center. 1, 2, 3. I'm just copying my sentence above. The middle 99.7% of data is represented by the range. What are those numbers? 39.7 to 333.1. Okay. What percent of data will be greater than 235.3? So they want to know the red region. And again, you can just use what we did above, but here in green, these 2 dots represents 1 standard deviation, so that's 68%. And then that's the x, that's the x. So again, you add all these up, 16% from here. Whoa, what is that thing? The ruler's attacking us, guys. Go away, go away. There. And that's 68, and then this one is 16%. So greater means going towards the right. That would be 16%. 16% of the data will be greater than 235.3. All right, what range of values is represented by the upper 2.5%? Okay, this one's tricky because it's not part of the empirical rule, but the closest one you can get to the empirical rule is what? Here in blue, right? This is 1, this is 2, 1, 2 standard deviations away. This represents 95%, the blue. So think of it as x plus 95 plus x, 95 plus 2x equals 100. So subtract it, 2x equals 5. That means x equals 2.5%. So that, what value though? The upper, so that means going towards the right, so it would be this number. These 2 numbers. Let's see, that says try again. The upper 2.5% of the data is between, we said that in yellow, 284.2 and 333.1. Let's move on to 8.46. Okay, we have a formula, and the formula that we need is z equals x minus mu over sigma. Okay, so this is a standardized score. And I'm going to highlight Z and standardized, that's why it's Z. Our X is our observed value, whatever they give us, observed value. Okay, this is the mean, and this one is the mean of the sample. We've been talking about note we were saying that the mean of a population would have been x bar, population mean. And then down here is the, let's get my color. This is the standard deviation. Of the mean. And basically we're just going to use algebra to solve. Always, say it, always write down the formula. So z equals x minus the mean over the standard deviation. Just plug and chug. Find z, so that's what we're trying to find. What is z? This is what we're trying to solve for. The observed value x is 24 minus the mean, so 19, over the standard deviation. So this would give us a z-score of 24 minus 9 is 5, and then 5 divided by 3.8 gives me, go around to the nearest thousandths, we'll be fine, 3 decimal places. It was 3.157. Okay. All right, tells you in the directions, find the z-score for the standard normal distribution. Skip one problem. So go ahead and take one problem, just put an X through it. And then we'll go over those together. All right, let's go ahead and put our formula down. I know it's your favorite, here it comes. Magic. Magic. All right. Okay, it's telling us that the mean standard deviation is 9.8. And our expected value, our given value, observed value, I mixed up the colors, didn't I? Sorry. The observed value, let's do that from the formula above, is 55.4. That's the top part of the fraction. And then the mean of the sample is 68.34. And it's okay to get a negative number. Put that into my calculator. Don't do it all at once. 55.4 minus 68.34. Press equals. You get negative 12.94. Don't touch anything in the calculator. Press divided by 9.8. And I get a z-score of negative 1.32. So box your answer. Okay if you get a negative z-score. We'll talk about using a table in the next lesson, but let's finish up these problems. We're still trying to find the z-score, and our observed value is 42.8. And then our mean is 68.2 over our standard deviation. And our standard deviation is 11.8. 11.6. And let's get a z-score. 4280 minus 68.2 gives me negative 25.4. Negative 25.4 divided by 11.6 will give me negative 2.19. A standardized score of negative 2.19. And let's try question number 10. The standard deviation is 11.6. The observed value is 119.2, and the mean is minus 112.4. Let's put that in and see what we get for our z-score. 119.2 minus 112.4, 6.8, divided by 11.6. I rounded. More numbers the better, but that's okay. That's sufficient. All right. Let's move on to section 8.47.
Steps to calculate a percent. The first thing I want you guys to do is draw a picture. Draw a picture of the normal curve. You guys remember this guy? Oop, mine's kind of scary. Okay, draw that. Number 2, write down that formula that we just wrote down. Every single time. Step number 3, we're going to go from a z-score, solving for z, to a percent. And this is where we would use our chart. Let's write that below. Use chart. Use that chart right there. Okay. I'll show it to you guys in a second. It looks kind of complicated, but we'll use a smaller one, a smaller version of it in this example. And then lastly, go ahead and just solve. Okay, let's try this example. Calculate the percent of adult men taller than 70 inches, given that the adult men's heights are normally distributed and the mean height is 69.3 inches with a standard deviation of 2.8. Okay, the first thing I'm going to do is I'm just going to draw a normal curve. Okay, then I'm going to look for the measure of center. The measure of center is my red one, which is the mean. So there I see the mean height. Switch to a pen. So again, that goes right in the middle. So what I'm doing is I'm just, step number 1, I'm just drawing my picture. Okay, then I'm going to use the standard deviation, which is orange. Remember, this would be a +1 standard deviation or +2.8. 2, 3. So let's write that. Standard deviation is 2.8. And the observed value is 70. So our example, x equals 70. Okay, so what did we just do? Number 1, this is my picture. Check. Let's write down the formula. Here's our formula up here. Z equals x minus the mean over the standard deviation. Okay, so my x value is 70. My mean value is 69.3. And the standard deviation is going to be 2.8. Okay, so let's just write in those values. X was 70, the mean was 69.3, and then the standard deviation is 2.8. Okay, all right, I'm going to go ahead and get a now I need to figure out the z-score, or just the z value. So you will get 0.7 divided by 2.8 And if you put that in your calculator, is 0.25. So let me also show you what I downloaded there. I'm on an iPad, and this one's called Graph and Calc 83. Graph and Calc 83. It mimics a Texas Instrument 83 calculator. You can go ahead and get one. I would recommend getting a graphing calculator. It's best if you have a physical keyboard, like you have a calculator in hand, but if you need to use the app, then you can. Okay, I have a z-score of 0.25. Okay, now we need to figure out a percent. Now, this is a standardized table here. And let's read what it says here. Table entry for z is the area under the standard normal curve to the left of z. So basically, you're finding the shaded region. The chart will help you find a shaded region, and you're going from the left to the right. That's up to that z-score. So basically, when I look up this value, it's going to find that yellow shaded region. Okay, let's go ahead and look for z equals 0.25. Okay, over here you have the tenths, and then up here you're running by the hundredths. So to give you an example, in blue, let's just say I want a z-score of 0.13. This would be 0.10, and this would be 0.03, because if you add those together, you get 0.13, and so you come down here, and that would be the value. Z equals 0.13 would give me a shaded region. That shaded region would be 55%. Okay, so in our example, we're trying to find 0.25. So here, so this is in the 20s, this is 20, 21, 22, 23, 24, 25. And that is the score I need, 59.87. I'm just going to write that down. Well, let's note on here. So where is 70 inches on our picture? Well, if you add 2.8 here, this would give us 72.1. And 70, the observed score, is between 69.3 and 72.1, so something like this. Let me just quickly shade that in. So basically what I'm trying to do is I'm trying to find this blue shaded region. And with our z-score, we just found that value. The value there in orange is 0.5987. Remember, going from left to right, so this represents 59.87. And here's a big idea. Let's pick yellow. If you ever needed to find the other side, I just want you to write this out so you know it. Blue plus yellow equals 1. The area under the curve is equal to 1. So if you know that blue is 59.87, you can subtract it from both sides to find the yellow. Because remember, the blue plus yellow equals 1. Okay, we did step number 3 here. And that's a 3. Can I write a little bit nicer? That's going from a z to a percent. And we got a z-score of 0.25 using the chart is 59.5987, which is 59.87%. And I have that there. And basically now we need to solve. Well, it wants to know, and this problem we have to, it wants taller. Taller means, or more, is going towards the right. So they do want us to find the yellow. So I'm just gonna 59.87 plus the yellow equals 1. And if we just subtract 0.5987, we will get the yellow to equal 59.87, 1 minus 0.5987. That gives me 0.4013. Because remember, if you add those two values, I'm just trying to prove that to you, that they equal 1. So 4013. Remember, to go from a decimal to a percent, you just move it over, you multiply by 100, and you'll basically get the yellow to be 40.13%. Gonna double box it. Okay. So basically that means that what percent of adult men are taller than 70 inches? 40% are taller than 70 inches. And so that was example A0. Make sure to draw the picture, formula, z-score, look at the chart, percent, and then solve. Okay, let's go ahead and move on to now A1. For A1, we have to use the numbers given to us, which is up here in direction number 3. Calculate each percent using a z-score table. The weight of bags of chips are normally distributed with a mean of 31 and a standard deviation of 4 grams. Okay, so let's first draw ourselves a picture. And in our picture, we have 31 is our mean. And then we're looking for 33. And more than 33 means we're going towards the right. Okay, so here's 33. I'm going to put a line here, and more than means going towards the right. So we're trying to find this shaded region. And to do that, I'm going to have to, remember our z-score table only helps us find what's on from left, starting over here. So basically what I'm going to have to do is I'm going to have to figure out the yellow, and that'll help us find the red. Okay, in the problem it tells us that the standard deviation is also equal to 4. Okay, so the first thing I'm going to do is we got a picture, and now we got our formula. Always write down the formula every single time. Z equals x minus the mean over the standard deviation. Okay, remember our x value is here. X equals 33. And then the mean is in blue, so that's a 31. And the standard deviation is 4. You're going to get 2 over 4, which is a z-score of 0.5. So I need to find basically z equals 0.5. All right, let's go ahead and click on this table up here. Okay. Oh, I have one. Let me press done. And we need to find that 0.5. So you'll recognize that the z-scores over here are negative. And we go over here, I'm looking for one that's 0.5. Okay, so this would be here and here. So you can write down those numbers: 69146, 69146, 69146, 69146. 69416. Okay. So here, this is step number 3. We're basically going from a z-score to a percent. And what we just found out is this whole yellow region is 0.69416. But I need to find more than, so I'm going to have to do some subtraction here. Okay, so essentially what we have is we have yellow plus red equals 1. And the yellow region we got to be 69416. And I'm just going to subtract that from both sides. And I will get the red region is equal to 0.385. And if I write a sentence to help you understand this, if you change it to a percent, 30.85% of bags of chips weigh more than 33 grams. Okay, that is A1. Let's move on to A2. I'm going to draw myself a picture. We know that the mean is 31. And we're trying to find ones that are less than 24. So x equals 24, so something like this. And remember, the shaded region is going from left to right. Okay. Step 2, we're going to use our formula. And that is z equals x minus the mean over the standard deviation, where our mean, our expected, or the, what did we call this thing? Observed value is x, which is 24, and the mean is 31. And then the standard deviation is 4, right? We're basically using 31 and 4 for the whole problem. So this will give us a score of, a z-score of negative 1.75. Okay. So now I need to take the z-score, so step number 3. We need to go from a z-score to a percent. So we're going to look up z equals negative 1.25. Okay, here's my table. That's nice because I'm already on the negatives. So negative 1.75 is here. And then I need to look here. So that would go all the way down this value right here. Negative 1.75 is 0.04006. 0.04006. 0.04006. Okay? That means that this red region represents 0.04006, and that's all I needed to find. So the red region is basically, remember, move it 2 decimal places, 4.006%. Let's use the same sentence as we did before. 4.006% of bags, weigh less than 24 grams. Okay, let's go ahead and move on to now A.
All right, let's go over A4. Remember now, we're using this information up here that the mean is 31 and the standard deviation is 4. So step number 1 is to draw a picture. And the mean here is 31. And the percent of bags that weigh more than 40. So 40 is up here. And we're basically trying to find this area. Now remember, the z-scores will only find percents going from left to right. So essentially what we're going to figure out is basically this yellow area. And we'll use that to subtract it from 1 to find the green area. So step number 2 is to use a formula. z equals x minus the mean over the standard deviation. So the mean was 31, standard deviation was 4, and then the value we need is 40. And if you recognize what's happening, some kind of hints here is when you put the standard deviation and you get a z-score, you're going to get a positive number, right? 9 divided by 4 is a positive number. And that should tell you that it's over here to the right. Okay, so 9 divided by 4 will give me a z-score of 2.25. Okay, this is now the step where we are basically looking from a z-score to a percentage, and I'm using the chart. So let's go ahead and look at the chart here. 2.25. Let's pick a color hopefully we have not used, maybe yellow. Okay, so here is 2, and here is 5. 98778. 98778. Okay, basically this chart tells us a percent. The standardized score, the z-score tells us a percent. So the yellow is equal to that amount. So if you think about this, let me write it out here. So right now we're doing step number 4 is we're just going to solve. I'm trying to find the green area, and I'm going to have to do yellow plus green equals 1. The yellow is equal to 0.98778. And if I subtract this from both sides, we're going to get the green area to be 0.0122. This means that there is a 1.22% chance that the chip bag, now I'm using the sentence, right, weighs more than 40 grams. And that's A4. Let's try A5. The percent of bags that will be discarded because they weigh less than, so that means it's going towards the left, 2 standard deviations below the mean. Let's get a picture. Here's my curve. The mean we got from the directions is 31. Okay, so using the standard deviation, remember 2 standard deviations below means a negative, so going left. And then what I'm doing is I'm just subtracting 4. So this would be 27, this would be 23. So it doesn't say 23, but I figured it out by subtracting 4 twice, because that's 2 standard deviations below. Here's another way of figuring out 2 standard deviations below. Well, we know the standard deviation is 4 in this problem, so that's minus 8 from the center. So 31 minus 8 is 23. So basically what we're doing is we're just figuring out this red area. So 2, let's go ahead and use the formula. Z equals x minus the mean over the standard deviation. Again, I got 23. I got 23 by subtracting 2 standard deviations away from the center. The mean is 31. And our standard deviation is 4. So this will give us -8 divided by 4, which is -2. And we already knew that, right? We already knew that it was -2 because it's -2 standard deviations away. Okay, so this is now our third step, where we're going to change the z-score to a percent. Z-score to a percent. Okay, so from here, I'm going to go ahead and use our chart. All right, -2 is here, and 0 is right there, so 0.02275. 0.02275. That's actually our answer. 0.2275, 0.2275, 0.2275, 0.2275. Okay, that represents our red area. Remember, if you multiply this number by 100, you get a percent. So there is a 2.275% chance that a bag of chips will, now I'm just using the sentence above, right? Will weigh less than 2 standard deviations below the mean. And this is our answer. Let's go to A6. All right, the first thing we're going to do is draw a picture. And remember, we get the center or the mean from the directions. It'll tell you the mean is 31. And you need to locate 37.25. So that's just a number bigger than 31. So you can just arbitrarily put it here. And it says weighs less, which means we're going to find a percent under the curve using our z-score. So let's write down the formula. Z equals x minus the mean over the standard deviation. That is our observed value. Our mean was given in the directions, and the standard deviation was 4. So I will get a value that is z equals 6.25 over 4. So I have a z-score of 1.5625. And I'm just going to round. It's approximate. So a z-score of 1.57. Okay, step number 3 is to go from a z-score to a percent. And we do that by looking at the chart. So let's go ahead and look at the chart. Okay, I have the negatives. So if I go to the second page, I get positives. And I have, we said 1.57. So down here, let's write that number down, 0.94179. All right, our value is 0.94179. Okay. So that is the green area. So number 4 is solving it. Well, remember, the z-score is always going from left to that number. So the green area is basically 0.94179. There is a, remember, just multiply by 100, 94.179% chance a chip bag, which is a big number, right? 94% chance weighs less than 37.25 grams. A G. Now I'm just going to write down the steps for a TI-83 calculator, and I'll tell you guys my Apple iOS or iPad. The app is called Graphing Calc 83, and I'll show it to you guys in a second. But let's get some directions down. We're going to click this button called Second, and then we're going to hit Vars. And I put a box around it because those are kind of like the buttons you press on the calculator. And then you're going to look for something called Normal CDF. Basically, that stands for a normal distribution. C stands for cumulative density function. And then you're gonna, when you get old like me, you want to use something called plums. Eat lots of plums. And what that stands for is this. And the nice thing about the app I'm going to show you is it kind of tells you what it means. Okay, plum stands for, P means the probability, but you will just use norm CDF. L means the lower bound. U means upper bound or boundary. M stands for the mean or average, and S stands for the standard deviation. And again, the P, you're basically finding the probability, right? Just as a review in the normal distribution curve, do you believe in ghosts, right? And so it's always starting over here to the left up to this value. So if you wanted to find the area under this curve, this green here, you would get this value. That's what it's doing. Okay, let's get some steps for the Desmos, and then we'll try that example with an example. Okay, so the first thing you're going to click on is functions. And you're also going to look for something called normal distribution. And you're going to put in there the mean, comma, standard deviation. So again, that is the mean, and this one is the standard deviation. Okay, and then all you need to know for Desmos is the box is equal to your area. Okay, it'll be on your worksheet, but I'll just read it out loud. Let's calculate the percent of adult men taller than 70 inches. We know, given that the adult men's heights are normally distributed, and the mean is 69.3 with a standard deviation of 2.8. Okay, I'm going to show you guys first the Graph and Calc 83. There it is, Graph and Calc 83 is that black swirl one on the right hand side. And so the calculator commands were second, which is in the top left, it's yellow. And then I'm going to press vars, which is below the down key. And then you're going to click on number 2 where it says normal CDF. And in white there it says normal CDF, lower bound, comma, upper bound, comma, mean, comma, standard deviation. So this is our plums. The P stands for the percentage, or we call it also fancy as a p-value. And in this problem, okay, so we want to find taller than 70. So my lower bound is 70. And then we're going towards the end. So here, you can just type in like, you can just type in like 99,999. And our mean is 69.3. And our standard deviation, comma, is 2.8. And we will get this number as our answer. The answer is 0.40, you round out 13, which is like 40.13%. 40.13%. There is a way to kind of give you a visual, well, make sure we understand. We were calculating this portion. So the answer is point. So normally how we did it before is we found the area of the green, green plus black equals 1. And you know, we would do the math and then we'd find the black to be that answer, but the calculator can calculate it for me. Does that make sense? All right, let's try the Desmos app. So there's my Desmos app. Okay, so you're going to click on the box. You're going to click functions in the bottom right. And then you have a bunch of menus, trig, stats, distributions, and miscellaneous. You can go to distribution, dist, D-I-S-T, and you want to click on, there's 2 of them, the normal dist or distribution, so you can click on that. And isn't this cool? When your standard deviation is, you can put in there, it's already in there, but it's 0, comma, 1, close the parentheses, and you click on find cumulative probability, CDF, it will shade it. And we talked about how our answer is in the box, which is 1. The whole purple area is 1. So let's go ahead and press backspace and put in our numbers now. We basically want our mean is 120, comma, 12, close the parentheses, and then our minimum we want, sorry, I was looking at the wrong thing. Let's try that again. Functions, normal distribution, let me start it over. Functions, normal distribution, and our 69.3, comma, no spaces needed, 2.8, close the parentheses, and then we want to find the cumulative, so check it. And our minimum we wanted was 70, and our max we want is some really big number. And if you click the magnifying glass to the left there, the cool thing is it will show us what it's shading. And you notice the answer in the box is still 0.4013. Okay, so this is using technology to figure out our answers here. In this case, again, we wanted the heights of men who are over 70, and that was the black area, and we found it in 2 ways, using either TI-83, Graph Calc 83, or if you have a regular TI-83 calculator, you can use that, or any TI-84 plus, all that stuff, or the Desmos app. All right, to review using either the TI-83 or Desmos, let me go use color here. Let's say we're trying to find the black area. This is something called our lower bound or boundary, and this is the upper boundary. If you're ever going towards like infinity, just use a really large number. I use something like 99,999. And if you're using something like, if you wanted to say find the green, and this would be your lower bound, negative infinity, you don't have that in your calculator, so you just type in like negative 99,999. All right, let's try B1, and the directions are up there in direction number 3. Determine each percent using technology. The systolic blood pressure for women is normally distributed with a mean of 120. Let's write that down. And a standard deviation of 12. Okay, let's do the same thing we did before. We're going to draw a picture. Here's my picture, my curve, my mean is in the middle. And I want something that is what? Less than. Less than means, we learned previously, means going towards the left. So basically we are finding out this picture right here. So again, this would be my lower bound, which I'm going to use like negative. You want to really use negative infinity, but we don't have that. And then here is actually my upper bound. Okay, let's go ahead and try that. Remember, we're going to use our acronym PLUMS for the TI-83. So second VARS, norm CDF number 2, negative 99,999. And we're, that's going to go all the way up to 120. And then our mean is 120 and our standard deviation is 12. And our answer is 0.5 or 0.50, or which is 50%. Add 0, multiply by 100. That yellow curved area is 50%. For 50% of women will have a systolic blood pressure less than 120 millimeters per Hg. I know what that is. Let me show you guys how to do that on the Desmos. Start over like you don't know. Functions, distributions, normal distribution right there. And then I'm going to type in 120, 12. And I'm going to check mark cumulative probability. And my minimum already had it in there. So Desmos already has the negative infinity. My max there, we want it to be 120. And you can see the answer in the box, and you can click the magnifying glass, and that's what you need to shade. So that was question B1. B2, again, our directions from above, we have a mean of 120, standard deviation of 12. Let's determine the percent of women with a systolic blood pressure between 125 and 140. Let's do the same thing, draw our picture. And our mean here is 120. 125 is here. And 140 is here. This is green. So basically we want to find this region here in yellow. Okay. So for my calculator, instead of using a formula, my calculator commands, I just want to note that this here is my lower, and this is my upper boundary. All right, let's go ahead and put that into our calculator. Here's a cool trick. If you already have normal CDF in yours, you can just press second enter. And what it does is it's going to repeat the entry, but you're going to have to go back and change some numbers. So we wanted a number at 125 to 140, and you can just press delete, and I already have the mean and standard deviation, and our answer is 29.06. 29, or you round up, 29.07. You could put the calculator commands in there if you wanted to. So my plums, my lower was 125, upper 140, mean of 120, standard deviation 12. And that should say norm CDF. Let's do that with the Desmos now. So functions, distribution, normal distribution, 120, 12. There's my curve. Close the parentheses, click on it. Then I want my minimum of 125 to 140. And there's a shaded area. And then if you click on the magnifying glass, it'll tell you there's an answer in the box, 0.290, round up, 7. So we don't have to use the table now, so I can just write an answer. There's a 29.07% chance that a woman's, I don't know what systolic means, systolic blood pressure, that's a P, I guess, is between 125 and 140 millimeters per Hg. So there's our answer. Let's move on to B3. Same thing, let's go ahead and draw ourselves a picture. And our mean is 120, standard deviation is 12. And let's go ahead and figure out, we want less than 93. So is 93 less than or more than 120? It's going to be less than, so 93, that's where I'm putting it there. I'm not putting it to the right, I'm putting it to the left, it's a smaller number. And less than means to go towards the left. So basically, this is our region. To get a calculator command, this is my lower bound. So something like negative 9,999, and this is my upper. So again, the calculator command is going to be norm CDF, and this is where my plums is. My lower is negative 99,999. My upper is 93, comma, my mean is 120, and my standard deviation is 12. So there's my calculator command. Again, you can just press second enter, or we can just do it again. Second vars, number 2, CDF. And we wanted in this problem negative 99,999 to 93, comma, mean 120, comma, standard deviation 12, close parentheses, boom. And if you want to (1.22%). See if we can get the same thing over here. Okay, so the great thing is you already have all the information from the previous problem. If you don't, one mean, comma, standard deviation tells you, and then the minimum, we're just going to delete this. And we wanted that number to be 93. the same answer, right? Multiply that by 1.22%. .22% chance that a woman's systolic blood pressure is less than 93 millimeters per Hg's. And that's B3. Let's try B4. All right, B4 says a doctor would like a woman's systolic blood pressure to be within 1 standard deviation of the mean. Okay, let's draw ourselves a picture. We know that the mean from direction number 3 is 120. Standard deviation is 12. Okay, within means there's an upper and a lower. 1 standard deviation. So I'm just going to put one here. Yellow is my lower. Green is my upper. And determine the percent one who meet this criteria. So remember, if you subtract 1 standard deviation, so subtract 12, right? That's why it's a minus 12 going to the left. You're going to get what? 108. Because if you go towards a 108 plus 12, you get 120. And if you add 1 standard deviation or add 12, you're going to get 132. Okay, so basically what we're trying to find is this area here. All of this. Okay, and then we already have our, there's our plums. Which is our norm CDF. Our lower is 108. Upper is 132, my mean is 120, and standard deviation is 12. All right, let's put that in. Second, VARS number 2, and we said 1 standard deviation, which was 108, and then we added from 1 standard deviation, 120, 132, comma, 120, comma, 12. And I think it's going to say 68. 68? How did I know that before I press enter? Let's try that over here. Okay, the numbers are the same. But again, we're just going to delete that one. Let's pretend you didn't know how to get there. Functions, dist, distributions, norm dist. 120, comma, 12, close the parentheses, click on the box, and I want this from 108 to 132. 68.27. That's interesting. Right, they're saying that this area is 0.6827, and you just multiply that by 100. Chance that a woman's systolic blood pressure is between, or is, I'm going to erase that because you're just copying that sentence right there in green. Within 1 standard deviation. Okay, Mr. Ang, how did you know the answer before pressing enter and not looking at the answer key? Oh, let's make sure we're clear, so I'm going to get a different color here. 1 standard deviation of a normal curve is the empirical rule, 68, 95, 99.7. Oh, got it. All right, let's try B5. A woman's systolic blood pressure is considered high if it is greater than 140. Determine the percent of women who have high systolic blood pressure. Let's draw a picture. In direction number 3, the mean is 120 and the standard deviation is 12. Okay, we're looking at greater than 120 or 140. I put 140 to the right of it because it's a number that's bigger, right? These are bigger numbers. That's bigger, smaller, or less than. So greater means going towards the right. We're trying to find out this blue area. Okay, so here, because the left side of the shaded region, this is my lower. This is going to be my upper. We said use the word like positive infinity or 99,000. And other parts of our plums. Our mean is 120, standard deviation is 12, and we need norm CDF. Okay, let's put it in. Remember, the trick is press second enter. Second enter. Repeats everything, and then we're just going to have to put it in there. So 140, 9999, 99,000, 120, 12. Boom. Multiply that number by 100, you get 4.78%. 0.0478. Let's try that over here. Again, the number's already in there, so you can just change these. And I'm going to get 140. Now, if you delete this, what did it put in there? Infinity, which is 99,909. Watch, you can also put that number in there. You still get the same answer. Okay, so what did we say? 4.78% chance that a woman will have a systolic blood pressure, then I'm just copying that, greater than 140. Like, I just got my blood tested, and it told me all these facts, just like we're writing right now. It'll tell me if I'm high, low, or within range. MMHG stands for millimeters of mercury. Yeah, millimeters of mercury. Hg is the scientific periodic table thingy. Okay. B6. Determine the percent of women with a systolic blood pressure more than 2 standard deviations below the mean. Okay, so we know from direction number 3 that the mean is 120. Standard deviation is 12. Let's draw a picture. There's my ghost, 120. Okay. 2 standard deviations below, so it means I'm going to subtract 12. This here represents 1 standard deviation, which is 108. And if you subtract 12 again, you will get 96. And it wants more than, so that's going towards the right, which means something like this. Okay, and then we gotta use our plums. Oh, way over here, huh? So my lower is gonna be 96. My upper is way over here. We said use 99,999. My mean is 120 and my standard deviation is 12. Let's put it in. I forgot all the numbers I just put in there. Second vars CDF, 2 standard deviations below 108, 96, comma, 2 going above, shading above, so that's 99,999, 120, comma, 12. And our answer is going to be 97.72%. All right, let's do that with this thing. All right, all the numbers are the same, but we're doing it to 96. And you can just erase this and it goes to infinity. And there's your answer. 97, 92. 97, 92% chance. A woman's systolic blood pressure is more than 2. Oh, a little nicer. Sorry, 2 standard deviations below the mean. And then they could have easily changed the problem and say less than, right? And you just go that direction.
We doing math today, ain't got time for no games. We doing math today, all work and no play. We doing math today, listen up and behave. We doing math today, we doing math today.